Alrighty guys, what we're going to do is we're going to help you out on how to do this momentum collision lab. First thing I'm going to do is draw what your setup's going to look like overall. Now the first thing you're going to have is you're going to have your kinematics rails set up to where just a small sliver at the end, we're talking just as little as possible, you're going to have one sphere resting on the edge and then one sphere up top. Now what I'm going to do is, as these spheres are going to go down the edge or down your ramp and they're going to collide, they're going to interact in a couple different ways. Well, depending on which one's more massive or how they collide, what you could get is you could get one sphere is going to be going some distance from the ground, right? And then the other sphere is going to go some further distance. All right. Now, with these two distances, we have to make sure that we're keeping our annotation separate. So this first distance we're often going to denote as D1. This is going to be D2. With this whole collision system, what we can do overall is find that the momentum before the collision is going to equal the momentum after the collision. Well, how do you find that exactly? If I know the mass and the velocity of the ball right here, we'll say mass and velocity here, or if I know the momentum before, this part becomes pretty easy to calculate, pretty straightforward. This would just be using your energy system setup. It's where you would say that the potential energy at the top of the ramp is going to equal kinetic energy at the bottom. So with that, you can then record height and mass of the ball. From there, you can know your initial velocity of whichever ball is falling down. This you would then plug in over here. Mass of the ball times initial velocity would get you initial momentum. For the other half over here, what we're going to do is put a little box around all this, and this will help us understand what's going on. And that is, we have some kinematics here. If I know for each individual ball, if I know that the height that these individual spheres fell, let me do a different color real quickly. Let's call this height right here. All right. I can then use kinematics to help me figure that out. So what I'm not going to do is give you all the information here, but I will give you a big heads up on how to do this. We're going to use kinematics. From there, you need to find that the time it took for the ball to hit the ground. After you know time, then you can then calculate final velocity. Now I'm going to say final velocity here because it's the velocity after this collision. If I know the velocity of each ball, let's call this the velocity final of ball 1 and the velocity final of ball 2 after the collision, you can then use that to find the momentum of ball 1 and the momentum of ball 2. If you think you're good there, then you're good there. What I'm going to do is now, here in a little bit, give the next hint on how to do the next part. How do you exactly go from time to velocity final, so on and so forth? Well, the first bit here will be to use your kinematics formulas. So I'm going to stretch this and get out of the way real quick. Let me close on that. And let's do the whole screen. Let's go the other way with it. There we go. So what do I got over here? Kinematics is going to be, you're going to record delta y. And we're going to say that the initial velocity in the y direction times time plus 1/2 at squared. Your delta y here would be the height you recorded. So you can then say that the time it takes this to fall is going to be, let's do a little bit of algebra here real quickly. That'd be delta y. Initial velocity in the y direction once the ball leaves this horizontal plane is going to be 0 plus 1/2 at squared. Rearranging this, a little bit of math magic, you got the time that it takes to fall, this part right here we're looking for first, to be equal to 2 delta y over gravity. And all that's going to be square root. Multiply by 2, divide by g, and you can find time. Once I know time, then you can then plug this again, looking in the x direction, and say initial velocity in the x direction times time plus 1/2 at squared. This gets you your, using your delta x, you can get initial velocity in the x direction. So we'll call this d1 equals initial velocity in the x direction times time, which I'm going to call square root of 2 delta y over g. Alrighty. With that information, we can now rearrange this whole situation to find initial velocity. Now, what I'm going to call this initial velocity of leaving this horizontal plane going to be the final velocity, or the velocity after the collision. From there I can find individual velocities, from there I can find individual masses, and then what you're able to do is compare the system of before equals afterwards. So if I write the whole system out, we have momentum before equals momentum afterwards. Sorry about that. And I have mass 1, velocity 1 plus mass 2, velocity 2, where your second ball is not moving at all, so this is going to come out to 0, and you have two objects after the collision. Mass 2, velocity 2. Overall, this is going to equal 0. This part right here, you're going to find using the little tidbit I've given you over there. And to find the last part of these two momentums, you're going to use your kinematics that we used over here. Good luck. If you have any questions, let me know.